Hi folks, lesson 1.2 is trigonometric functions of an acute angle. So today we're going to introduce all of those fun functions which you may have come across in your math career: sine, cosine, tangent, cotangent, secant, and cosecant. And we're going to use the right triangle to introduce these. So this picture right here, it demonstrates the triangle. So we have angle A, angle B, and angle C. The reason why we're dealing with acute angles is because angle C already has 90 degrees. So between angle A and B, we know that we're dealing with something, the sum of angle A and B from lesson 1.1 is 90 degrees. So it's going to be less than 90 degrees for each angle, meaning it's acute. So what I'm going to do is I'm just going to show you all of the different functions. And A in this case is going to be our reference angle. Because A is our reference angle, the side opposite A is this length, or this side A, or we can also think of it as BC. Okay? Now the leg that's touching A in this case is the adjacent, and I always say leg. Remember that the leg, when I say leg, it's something that is touching this right angle. The hypotenuse is always opposite the right angle. Okay, so that is always the hypotenuse. These are both legs because they're touching the right angle. In regards to this angle A, the adjacent leg is the one that's touching the angle. The opposite leg is the one that is across from that angle A. Okay, so the first function, sine, and we spell that S-I-N-E. The sine, and we just abbreviate it to S-I-N, of angle A is equal to the opposite leg, so the opposite leg over the hypotenuse. Okay? So once again, we're just referring to sine A and the angle A. We can use the angle B, and we will do that soon. Next, cosine. Cosine of an angle A, of the angle A, is equal to the adjacent leg over the hypotenuse. I'm going to abbreviate that. Okay, the last one is tangent. The tangent of the angle A is equal to the opposite leg over the adjacent leg. So see how tangent doesn't use hypotenuse here? We're just using both of the legs, the opposite leg over the adjacent leg. Cosine involves the hypotenuse in the denominator for both cosine and sine. Okay, so there is a fun way to remember this, a nice way. It's the SOHCAHTOA, which you probably have heard of. So for sine, it's the sine is opposite over hypotenuse. So we say so. So that's the opposite leg over the hypotenuse. Okay? Cosine, C, is the adjacent leg over the hypotenuse. That's ka, like the raven. And tangent is TOA, opposite leg over the adjacent leg. So that's just a nice way to remember your trig ratios. And I'll write that in. That's adjacent over hypotenuse. And you can sing a song. It's SOHCAHTOA. This is what my geometry teacher sang for me back in high school. SOHCAHTOA, 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 SOHCAHTOA. You get it? Is it a good song? Okay, so that's just a way to remember the ratios. So remember, sine is opposite over hypotenuse, cosine is adjacent leg over hypotenuse, and tangent is opposite over the adjacent. Now, we have to ask, where does secant, cosecant, and cotangent fit in? Well, the interesting thing, folks, is that all of those three functions that I just mentioned are the reciprocals of sine, cosine, and tangent. So really, you only have to memorize these three ratios, and then you just make the connection, knowing what function is the reciprocal of sine A, and that function is cosecant. Okay, and the function that corresponds to cosine is secant. And let me just spell it out, so cosecant, secant, and then guess what corresponds to tangent? What's the reciprocal of tangent? Yes, you've got it, cotangent. So for our functions, this is in your book, but I would write it down. Once again, the sine is equal to opposite leg over hypotenuse. The cosine is equal to adjacent leg over hypotenuse. The tangent is equal to the opposite leg over the adjacent leg. Remember, once again, tangent deals with both of the legs and no hypotenuse. The connection now, sine and cosine, or excuse me, sine and cosecant. And we can say that cosecant of angle A is equal to 1 over the sine of angle A. So let's do a little algebra for fun. So that means that we know that sine of angle A is equal to A over C, right? So that's 1 over A over C. Well, that just gets flipped, so that's equal to equivalent to C over A, which is what cosecant is. All right, so see that connection. Cosecant is related to cosine. Once again, it's the reciprocal. So notice the B over C, and this is the side. This is C over B, and then we also have tangent, which is related to cotangent. Okay, so really you only have to kind of memorize the three functions, sine, cosine, and tangent, and then to see which one is the reciprocal. The cosecant goes with sine, cosine goes with secant, and tangent goes with cotangent. And use SOHCAHTOA. I still use that to this day. It helps me tremendously. And here is the reciprocal relationship with cosecant equals 1 over sine, secant 1 over cosine, cotangent 1 over tangent, and so on. I don't know if this helps, but cosecant, a C and an S, these guys are opposites. Sometimes students oftentimes mistake and think that sine A goes with secant, but it doesn't. Notice that secant corresponds to cosine. It's easy to remember cotangent and tangent. So we're going to use number 10 as an example. This corresponds to your assigned problems 1, 7, and 9. So what you have to do is find the values of all the 6 trigonometric functions of angles A and B in the right triangle ABC using figure 1, 2, 3, which is here. So I chose this one because they only give you 2 sides, but we can find the third side using Pythagorean theorem. So we know that angle or length AC or B is equal to 7, C is equal to 8, and if we do the Pythagorean theorem, we have 1 leg squared, that's B, plus we need to find A squared, that's equal to 8 squared. So that's 49 plus A squared, which is equal to 64. If we bring the 49 over to the other side, that gives me, I did my math correctly, I believe it's 25. Take the square root, so A is equal to 5. So this is a Pythagorean triple of 5, 7, 8. Okay, so now we know that A is equal to 5. So we're just going to start writing all of our ratios. We have that the sine of A, as from before, is equal to, so opposite over hypotenuse. So I'm going to say that that is the opposite side is 5. In regards, remember, I'm using this angle A. The opposite leg is over on this side, BC, okay? So that's 5 over the hypotenuse. The hypotenuse is 8. Cosine, that's ca. So the cosine of A, in regards to this angle, the cosine of A is adjacent, so that's this leg, from here to here over hypotenuse. So that would be 7 over 8. And tangent of A is equal to the opposite from A, so that's the opposite leg, A or 5 over 7. What corresponds to sine? What's the reciprocal? Cosecant. I almost said secant. So the cosecant of A is equal to 8 over 5. The secant of A, remember, is equal to 8 over 7. And the cotangent, the cotangent of A is equal to 7 over 5. Now we have to find all of the 6 trigonometric functions for angle B. So once again, we're dealing with the same triangle. This length is 7, this length is 5, and this length is 8. Okay? Now what I sometimes tell students to do is put your finger even on this angle B. What is the side that, or the leg that's opposite B? Now it's this side. Does everybody see that? So this is the opposite leg to this angle with respect to this angle. The adjacent leg is the one that's touching the angle, okay? And the hypotenuse is still the same. So if we say the sine of B, that's equal to, so opposite, so that's opposite leg, which is 7 over hypotenuse, 8. The cosine of B now is the adjacent leg. So the adjacent leg in respect to angle B is 5, or A. Okay? So it's 5 over the hypotenuse, 8. And then tangent of B is equal to the opposite leg of tangent, which is 7, over the adjacent leg, which is 5. And then from there, you just write the corresponding functions. Cosecant is equal to 8 over 7. Secant of B. I put A. Excuse me, that should be a B. The secant of B is equal to 8 over 5. And the cotangent of B is equal to 5 over 7. So you guys are assigned 11, 13, and 15. I'm going to show you a couple of examples for this sort of exercise to find the values of the other 5 trigonometric functions of acute angle A given the indicated value of one of the functions. The first one, sine of angle A is equal to 2 over 4. So what you first want to do is you want to draw your triangle, your right triangle. Sorry, it's not the prettiest triangle. Here's angle A. Here's angle B, then an angle C. Remember, sine of A is opposite, so I always remember, so is opposite leg in regards to this angle. This is our reference angle over hypotenuse. Okay, so what they're saying is the opposite leg from angle A is 2 and the hypotenuse is 4. We need to find this side B. Okay, so what we're going to do is use the Pythagorean theorem. 2 squared plus b squared is equal to 4 squared. 2 squared is 4 plus b squared is equal to 16. B squared, if I bring the 4 over to the other side, is 12. Take the square root. So that tells me that b is equal to, well, if I break down 12, 12 is 4 times 3. This is simplifying a square root. What's the square root of 4? It's 2. So it's 2 rad 3. Okay, so now I know this side. So you first find the missing side, so it's 2 root 3. And now you can find the other trigonometric ratios. So we have sine already, so we can just rewrite it. Sine of A is equal to opposite over hypotenuse. Cosine, of A is adjacent, which is 2 root 3 over hypotenuse, which is 4. And yes, you can simplify that. So we're going to simplify 2 goes into 4 2 times. So if I simplify that, that's root 3 over 2. And then tangent, I'm going to write that, tangent of A is equal to opposite leg 2 over 2 root 3, which is equal, simplify that, 1 over the square root of 3. Oftentimes if you see this looking different, it's because they rationalize the denominator, and to do that you have to multiply the top and the bottom by root 3 over root 3. So that's equal to root 3 over 3. So you'll see that often. Okay, so now sine of A, what corresponds to sine of A? You got it. Cosecant of A is equal to 4 over 2. We didn't simplify this, did we? That's 1/2. Let's simplify that first. So then that would be 2 over 1, or just 2. Okay? Cosine secant of A is equal to 2 over root 3. If you wanted to rationalize the denominator, you could multiply the top and bottom by root 3 over root 3. That's just multiplying by 1. 2 rad 3. Square root of 3 times the square root of 3 is just 3. Okay? And then once again, with tangent, we have the cotangent of A, which is equal to 3 over the square root of 3. And so if we rationalize the denominator on that, we would multiply top and bottom by root 3 and root 3. So we have 3 root 3 over 3. Cancel those out. That's equal to rad 3. We're going to talk about similar triangles next, and I just observed that notice how sine A was equal to 2 over 4, and we use those sides 2 and 4. But since that simplifies to 1/2, could we use a triangle sine A, which is equal to 1 over 2, and if we did that, that would be opposite is 1, the hypotenuse is 2. If you did the Pythagorean theorem, that's 1 squared plus b squared equals 2 squared. So b squared is equal to 4 minus 1, which is 3. So that tells me that b is equal to the square root of 3. So this is a great example, because now do you see that the sides we have 1 square root of 3 and 2, and up here we had 2 root of 3 and 4. Do you see that all I have to do is multiply all of these sides by a factor of 2 to get these sides? Let's see if all of the ratios are still going to be the same. So that would be kind of a huge discovery. If we had the sine of angle A is equal to 1/2, and now we have the cosine of A is equal to adjacent, which is square root of 3 over 2. What did we find for, oh my goodness, look at that, the square root of 3 over 2. See how it simplifies to that? And then we have the tangent of A is equal to 1 over the square root of 3, and if we rationalize the denominator, that's the same as root 3 over 3. So is this a huge discovery? Yes, it is. Well, it's not a discovery, it's already known, but this connection is that it doesn't matter what the size of the triangle is. If you're dealing with similar triangles, I could have simplified this original problem number 14 to this and dealt with the 1 and the 2 and the square root of 3, which would save me some simplifying when I'm finding all of the 3 or all of the 6 trigonometric functions, okay? So if you can simplify and each of the sides by a factor of 2, go for it. Go ahead and use that. And this is a huge thing with all of trigonometry when using trigonometric functions. And we'll see it here because in the US we use inches to measure things and feet, but everywhere else in the world they use meters. So if you are in another country such as Germany, what is a measurement of 3 centimeters to you in Germany would be 3 inches to us. But as you can see, these triangles are similar. It's like 2.54 is the conversion for inches in centimeters, so that's the equivalent. So that would be what you would multiply in order to convert from centimeters to inches. So with similar triangles and this idea of trigonometric functions, you can see that when calculating trigonometric functions of an acute angle, you may use any right triangle which has angle A as one of the angles. That reason is that this angle A is congruent to this angle A, and that's a theorem with similar triangles, that if the triangles are similar, all of the corresponding angles are congruent in Euclidean geometry. And same with these, angle B and angle B is congruent here. And both of these are right triangles. So two special cases of triangles will show up a lot in this class, and one of them is the 45-45-90 triangle. So the first thing, this is from example 1.6. I'm not going to do it all. I just want to point out a couple of things. What they did was they took a random square that has sides of length 1, and they divided it in half. And since this triangle ABC is a right triangle, we know that the two other angles, this angle and this angle, the sum is going to equal 90 degrees. Since it's also an isosceles triangle here, both of these sides are equal, we know that the base angles are congruent, and thus that's why this is 45 degrees. We can use the Pythagorean theorem to find the hypotenuse, which is the square root of 2. 1 squared plus 1 squared equals the length c squared. So if you calculate that, that is the square root of 2. Okay, so this is a special 45-45-90, and then you can go from there. So if you wanted to look at, for instance, the sine of angle B, sine is so from angle B, what's the opposite in this right triangle? It's the opposite is 1 over the square root of 2. Okay, and you can read further but be sure to look at this example. This is a way to construct a 30-60-90 triangle, and what you do is you start out with an equilateral triangle where all sides are 2, length of 2. Then you construct an angle bisector right here, so these two angles are equal. Since an equilateral triangle, all angles are equal. If this is 60 degrees, this is 60 degrees, then each of these are 30 degrees. We know then that the opposite side, it bisects it equally, so this side is 1 and this length is 1. We can find square root of 3 the same way by using Pythagorean theorem. So it would be, if I call this side A, we have 1 squared plus A squared equals 2 squared. So A squared is equal to 4 minus 1, which is 3. So A is equal to the square root of 3, and you can go from there. So this is a special 30-60-90 triangle. This is also example 1.7, so read that example, please. And these are the general formulas for the two special triangles, the 45-45-90 and the 30-60-90. So if you remember this, suppose that in a 45-45-90 triangle, you know that this was 45 degrees, and this is 45 degrees, and this is 90. So if I said by chance that this angle right here, or this hypotenuse was, I don't know, I'm going to pick a number, 6. Okay? Well, what we could do is we could actually find the lengths of these two sides, and I know that they're equal because it's an isosceles triangle, by saying that 6 is equal to a square root 2. And if you solve for a, that is by dividing both sides by the square root of 2, you have 6 over root 2. You could rationalize the denominator by multiplying the top and bottom by the square root of 2 and the square root of 2. So that tells me that a is equal to 6 rad 2 over 2, or 3 root 2. So both of these sides then would be 3 root 2 and 3 root 2. Okay? Notice that a similar triangle to this, if I decrease these by a factor of 3, divide everything by 3, what do I have? I have 2, I have root 2, and I have root 2. So do you see that the sine of 45 degrees, in this case I'm going to actually use this 45 degrees, is opposite 3 root 2 over 6 from this triangle. And similarly, if I say 45 degrees here, I have that the sine of 45 is equal to root 2 over 2. So notice, if I simplify this, it's equal to root 2 over 2, and this is already simplified to root 2 over 2. So once again, I'm emphasizing that it doesn't matter if the sides are longer as long as they're proportional and similar triangles that you're dealing with. So the cofunction theorem, if A and B are the complementary acute angles in a right triangle, then the following relations hold. Remember that complementary means 90 degrees, right? That the sum of the two angles is 90 degrees. Those are the two angles here. So for instance, the sine of 53 degrees, you want to find for this directions, and you guys have the ones that I circled, you have to do those. So for 20, you write the given number as a trigonometric function of an acute angle less than 45 degrees. 53 degrees is greater than 45 degrees. So we're going to find the cofunction, the the function that is equivalent to this. So 53 degrees, remember to find the other angle, it's 90 minus 53 degrees, which would equal, if I do my math correctly, what is that, 37 degrees. So that means that this angle is 37 degrees, okay? You can either memorize the theorem or you can remember that, which is sine of angle A is equivalent to cosine of B. So we would say, okay, then the cosine of sine of 53 is equivalent to cosine of 37, so the cofunction. Okay, but why I'm drawing the triangle is I just wanted to point out that, see that sine of 53 would be opposite, excuse me. So opposite over hypotenuse. Okay, but the cosine of 37 would be the adjacent leg for cosine over hypotenuse. So do you see that these are the same? Because for the 37-degree angle, it's its adjacent leg. For the 53-degree angle, it's the opposite leg. Okay? And now for tangent of 26, for number 26, you're supposed to find an acute angle that's greater than 45 degrees. So if we do, once again, 90 minus 26, we can find the other angle, which would be, what is that, 64? So this is 64 degrees, okay? And if you look up here, tangent is equivalent to cotangent of B. So we can say that this is equivalent to cotangent of 64 degrees. And once again, think about tangent. Tangent from in respect to this angle is opposite over adjacent leg, right? If we do the cotangent of 64 degrees now, cotangent of 64, and remember it's the reciprocal, so cotangent of 64 is adjacent leg, which, see how these are the same in this case, over the opposite leg. So that's why they're cofunctions, and that's why they're equivalent. So the last example I'm going to show is number 34. It's similar to 33, and this is an online class, folks, and you guys are going to have to get creative. You can't always ask me the questions. So please don't hesitate to come up with something. There's always a clever way that my students can explain things. So just don't be afraid to go with your gut instinct. And I'm just going to go through this thought process on 34 with you and show you kind of how I think about it. So if A and B, these are angles, are acute angles, and A is less than B, explain why the cosine of A is greater than the cosine of B. And so for me to explain that, I had to just think about drawing a triangle. So a right triangle, so here I go. Like I said, there might be a better way to explain this, but this is what I'm going to do. And I know that angle A is less than angle B. So thinking about that, the side that's opposite this angle is going to be less than this side that's opposite. So if you say that this length here is just, let's just use a 3, 4, 5 triangle because that's nice. So here's, if it's less, then it's going to be this side is 3. The side opposite B is 4, and by the Pythagorean theorem, this length is 5. Okay, so I know that angle A is less than B, and it's kind of like the alligator opening up to the bigger side, so that means that the angle is also larger. Okay, so now I want to say, okay, what's the cosine of A? Well, the cosine of A with this is 3. Wait, no, it's not. It's the adjacent. So it's the cosine. Let me erase this real quick. The cosine of A is adjacent over hypotenuse. See, even your instructor makes a mistake. So cosine is 4 over 5, whereas the cosine of B, Remember, this is good practice. This is your, right here, cosine of B is your reference angle. Put your finger on angle B. Now what's the adjacent leg to that? That's 3. Okay, so the adjacent leg to angle B is 3 and the hypotenuse is 5. So just from this example, you can see that 4/5 is definitely going to be greater than 3/5. So for purposes of this class, if you can show me by an example, I will be fine with that, okay? This isn't a rigorous proofs class, so anything like that, get creative, and that should help you with number 33. This concludes lesson 1.2.